Hi guys. Today we're going to take a look at page 7 of the Unit 2 Classwork packet, and we're going to talk about another transformation called dilations. You'll recall last time we talked about a translation. A translation was a rigid motion transformation because, well, it may have moved the figure, but it didn't actually change its size, right? By contrast, a dilation, and this is where you're going to get ready to write stuff down, a dilation is a non-rigid motion transformation, okay, of a figure with respect to a fixed point called the center of dilation. So again, a dilation is a non-rigid motion. It's non-rigid because it's going to make it bigger or smaller. So the figures that I produce, they're not going to be congruent. By contrast, this is the third bullet point, the figures are going to be similar figures. Once again, similar figures, okay? That's looking a little bit ahead, right? Because we're going to look at similarity in some detail in Unit 7, okay? There's a formal definition for it, like all the angles, the corresponding angles stay the same, but the corresponding sides are proportional, which means just multiply by some scale factor. But I don't want to get too far ahead of ourselves. Now the scale factor, it's a fancy way of saying, like, by what do we have to multiply the original? So in other words, how many times bigger is it getting or how many times smaller, okay? And it's represented by the letter K. I don't really want to use the word variable. I prefer the word constant there, but I'm not gonna quibble, okay? K. So the coordinate rule, and I want you to write this somewhere in the margin because this is important. The coordinate rule for a dilation in the xy coordinate plane, as long as the center of dilation is at 0, 0, we'll talk about why that's important later, but for right now, you can just memorize this, is kx, ky. Now, if k is greater than 1, we would say that this is an enlargement, right? Think about it. If k is 2, that means it's getting twice as big. If k is 3, 3 times as big. By contrast, what if k is a fraction less than 1? So what if k is less than 1? Then we would call this a shrink. Or, alternatively, you could call it a reduction, if you prefer, okay? But again, what's the most important thing to take away from this? The most important thing is to take away that this is the coordinate rule for a dilation. Let me say that again. The most important thing to take away from this is that when we perform a dilation, this is the coordinate rule. Now, the reason that's important is that coordinate rule is going to make these problems really easy. Like with translations, the goal is often going to be the same. They're going to ask me to find the new coordinates after a dilation. Well, guess what? What that means is that all I do is I take the original x and y and I just multiply it by the scale factor. Let me say that again. To perform a dilation with center of dilation at 0, 0, all I do is I just multiply all the x's and all the y's by the scale factor, okay? Now, in order to see how this is going to work, let's take a look at an example together. And we'll actually do this one on the xy plane so you can see how it gets larger, or in some cases smaller. So we're going to take a look at page 8, page 8, example number 1. Okay? Once again, page 8, example number 1. Okay, so I'm actually going to write these coordinates down first, if that's okay with you guys. Just because, you know, I'm liable to forget stuff and get negatives wrong and all that good stuff. So, let's see, -1. Alrighty. I hope my marker's not running out already. That'd be really sad. Okay, so 2, 3, 4, 5. -5, 1. -3, 2, 3, 4. Okay, and then 2, -1. Itty bitty triangle. All right. Now, what they tell me, and that's triangle, let me make sure I label this right, RST. What they're asking me to do is they're asking me to find the new coordinates after the dilation. Now what they tell me here is that k equals 2. Okay, k equals 2. So that means that my coordinate rule is just gonna be 2x, 2y. I just plug the 2 in for k. Now, as to actually how to perform this, by far the easiest way is just to take that 2, and for each one of these points, what do you think I'd have to multiply everything by? Oh my god, by 2. So think of it as a giant just distributed property here, right? I'm just gonna multiply each one of these things by 2. So that means that my new points are gonna be -10, 2, -6, 8, and what do you guys think the last one would be? Oh my gosh, yes, you're right. 4, -2. So if I actually go out and graph this, 6, 7, 8, 9, 10, and then up 2, there's 1, -6, 8, so that's 4, 5, 6, 4, 5, 6, 7, 8. And then my third one, 4, -2, 3, 4. Okay. Notice what's really cool about this, right? It's like the figure is pretty much like the same basic shape, but it grew. And the reason that it grew was because the scale factor of 2 was greater than 1. If k, known as a scale factor, is bigger than 1, it's going to be an enlargement, or we could say a growth. By contrast, if it's less than 1, like if it's a fraction like 1/2 or 1/3 or something, it's going to be a shrink instead. Sometimes they're not necessarily going to give you, right? Sometimes they're not necessarily going to give you the graph. What they're going to do instead is they're going to ask you to just use the coordinates and the scale factor. So just to take a look at an example like that, let's take a look at example 3, okay? Where they don't give you a graph and they just ask you to find the new coordinates. So example 3 gives me 4 sets of coordinates, right? They give me -10, 2, -2, 8, 6, 2, and -2, -4. Awesome. And they tell me that my scale factor is 1/2. Okay, so what can I ask you to do on a test or quiz? Well, what I could do is I could ask you to write me a coordinate rule. So if I asked you to write me a coordinate rule, I would expect this: 1/2 x, 1/2 y. That represents the coordinate rule for a dilation by a scale factor of 1/2 centered at 0, 0. That's a whole lot of mumbo jumbo, which is a fancy way of saying we're just going to shrink the figure an itty bitty bit. Okay? So what do you think I'm now going to do with that 1/2? Well, I'm just going to multiply it by every single one of these pair of coordinates. Okay? So guess what? When I multiply 1/2 by each of these, I'm going to get -5, 1. When I multiply 1/2 by each of these, I get -1, 4. When I multiply 1/2 by each of these, I get 3, 1. And when I multiply 1/2 by each of these, I get -1, -2. Bam! Oh my gosh, can you believe how easy this is? Now, the only thing that can get a little tiny bit tricky is actually on page 9. On page 9, we have an example where instead of giving us the original coordinates, instead they gave me the new coordinates and they want me to go back and they want me to find the original ones. Let's see how this should work, okay? Excuse me. And let's take a look at example number 13. Once again, we're taking a look at page 9 of the Classwork packet, Unit 2 Classwork packet, example 13. Okay, so they tell me the scale factor, right? So they tell me that the scale factor is 3/2, and they tell me that the coordinates at the point after it's been performed are 3, 8. Okay. So here's what I know, right? I know that in order to get from the original coordinate, which I'll call x, y, to these, I know I had to multiply by this, right? So I'm going to write this coordinate rule. 3 halves x, 3 halves y. Oh my gosh. Well, if I know that 3 halves x equals 3, all I have to do is set up an equation. And to get rid of a multiplied fraction, I multiply by the reciprocal, right? And I get over here, x equals 2. By contrast, over here, I would write 3 halves y equals 8. To get rid of the multiplied reciprocal, multiply top bottom by 2/3. And I would end up with that y equals 16/3. Or, if you prefer to think of this as like a decimal, right? I could do 5 and, 1/3, or 5.3, repeating on forever and ever and ever and ever and ever and ever and ever. Okay? What else? For example number 15, okay? They're asking you to identify the scale factor, just looking at the graph. The easiest way to do this for now, okay, I'm gonna be very, very careful about this. The easiest way of doing this for now, when we have our center of dilation at 0, 0, is actually just to look at the change in coordinates. So for example number 15, take a look at D and D prime. So the coordinates of D prime are, 0, 2. So I'm gonna write that over here, 0, 2. My original coordinates for D are 3, 4, 5, 6. So 0, 6. Let me ask this. What do I have to multiply 6 by in order to get 2? Well, I have to divide it by 3, right? But that's the same thing as saying I multiply by 1/3. So that would mean that the scale factor is 1/3. Now, I'm kind of hesitant to actually show you that because it's limited to cases where the coordinates are being dilated by a scale factor that's centered at 0, 0. We may take a look later at some cases where the center of dilation is not 0, 0. In other words, the figure's not growing from the origin. It's growing from some other random point in space. So just be prepared. That works in the easy cases, but it may not necessarily work in the more difficult cases where our center of dilation is at a point other than 0, 0.